Now I am recording. Okay. So we just started at the beginning that in a linear system of equations, you will always have no solutions, exactly one solution, or infinitely many solutions. This is the form of homogeneous and non-homogeneous differential equations. And now you're all caught up. Okay. Anyway.
I have a quick question on linearity.
Yeah. Oh, sorry.
I was trying to figure this out last night and got a little confused. When we refer to a differential equation being linear, that is not the same thing as a regular equation being linear, correct? Those are two different.
So it's a little different.
As in the independent variable can be nonlinear in a linear differential equation.
Exactly. That's the sort of thing. Like for example, sine of x is clearly not like in any kind of straight line, but the fact that it doesn't contain any y's means that this is linear in the dependent variable. If that makes sense.
That makes sense.
Okay, cool. So yes, when we're talking about linearity of a differential equation, we're specifically saying this is a differential equation in one specific dependent variable. And all of the coefficients do not involve that variable in any way. Or I think technically, I took a class on modeling last year, and one of the examples that we saw, our professor gave to us written in terms, for example, with y, in terms where some of the coefficients were written with y, except we had additional information that allowed us to write those specific coefficients rather in terms of x. And that would also be considered linear. If it's possible to represent this thing not relying on y at all, then it is linear. Okay, anyway, yes, so that's the sort of thing that this section is talking about, exclusively linear things. And so all throughout these notes, I have linear oh, the poor toddler's having a hard time. But all through here, I have repeated homogeneous linear DE, non-homogeneous linear DE, linearly, whatever. Like, it's all talking about that, and it's very repetitive in this section. But it's because these things don't apply in other scenarios, and we want to make sure that you guys understand that. So yes, this has a unique solution. This is super nice because it means that if every one of these coefficients and g of x are continuous on some interval, and the leading coefficient a sub n of x is non-zero for all x along that interval, then an initial value problem subject to these constraints, where every derivative is taken into account, and you're plugging in the same x naught for every one of them, this has a unique solution for any given x naught lying in that interval. Okay, so example 1. Given that this is a 2-parameter family of solutions for this specific linear differential equation on the entire real line, show that there are no constants C1 and C2 such that the family satisfies the initial conditions y of 0 equals 0 and y prime of 0 equals 1. So how can we go about this?
Should we take the derivative with respect to y of the solution first?
Yeah, totally. Y equals C1 plus C2x squared. So y prime, and my primes are always a little messy. It's fine.
Sorry, how do I unpin your live notes? It's stuck. It's a little tiny box.
Let's see. I am going to pin for everyone this. Is that what you want?
It looks the same
no,
so
that's
far.
Not quite good. Gosh dang it. Let's see.
Oh wait, hold on. I think I figured it out. Never mind. Yeah, we're
I had not pinned. So you're saying pinning this video?
Yeah.
Yeah. Okay. So now it should be pinned for everybody at least. But yes. So the derivative of this, well, the derivative will be with respect to each term, right? So C1 will just go to 0. So this will be 2C2 times x, right? And we need the second derivative. Well, so the thing is, we don't technically have to check this in this problem, even though it's a good habit to get into. Y double prime will be 2C2. And so x times y double prime, 2C2, minus y prime, 2C2x equals 0. So we can check that this is a solution easily enough. But this problem specifically is saying, show that constants cannot be found such that this also satisfies y of 0 equals 0 and y prime of 0 equals 1. So what I am trying to do here in answering this question is saying, take this equation y and figure out whether we can also add the stipulations y of 0 equals 0 and y prime of 0 equals 1. What is the solution here? So, okay, if y of 0 equals 0, that is y of 0 will be c1 plus c2 times 0 squared. So this whole term disappears. This becomes just c1. If this is equal to 0, then c1 has to equal 0, right? Okay, so this holds. At the very least, C1 must equal 0 for this system to have a solution. Okay, so y prime of 0, we figured out here, 2C2x. Ah, dang, no, you were totally right. You were saying that we just needed the first derivative. I thought that you were trying to say that we needed to check this, but no, you just need that to plug in here. Okay, whatever. But y prime of 0 will be 2 times C2 times 0, right? Because C1, oh gosh, I don't think it even actually requires C1 to be 0, but right, this derivative doesn't rely on C1 at all. And so this is going to disappear. It's going to be equal to 0 for all x forever, right? And so there's no way to solve this second part of this equation. Okay, so there are no solutions. Why does this not violate the theorem that we just saw? Why does this not break the rules? Scroll up again. As a mathematician, that tells me that one of the assumptions that are necessary for this theorem were not met. So which of these assumptions were not met? We have,
Hold on. To clarify the theorem, what is the relationship between y sub 1 and y sub naught?
okay, so y sub 1 and y sub naught, y sub naught is just the labeling that we gave for the first y value, but y sub 1 is the sort of initial value of the derivative of y. That's just the notation that they used in the book. For myself, I did y prime sub naught and y n minus first derivative sub naught for all of those, but when I typed it up, I went with the book's notation. So the equation that we are using, this is x.
Sorry, is
double
it because
prime.
one of the leading coefficients is 0?
So it's not because of that.
Sad.
Even though, so it's intriguing. Okay. Let's see, minus y prime equals 0. So the requirements that we know have to be met here. We know that every a sub I and g of x are continuous on some interval. Well, in this case, these are all, well, not all constants, I guess. This first one is x, right? But that's certainly continuous. It's a straight positive line, right? This one is -1, which is constant. The y here, the 0th derivatives coefficient, or a sub naught, is equal to 0, but that's okay. That's still continuous, and g of x is equal to 0, so that's good. So this condition totally met on I equal to the entire reals, right? All of these are continuous on the whole real line. We need the leading coefficient is non-zero for all x on that interval, or on maybe only a portion of that interval, right? So our leading coefficient here is x. X is only non-zero when literally x doesn't equal 0, right? So the intervals that we have to break up into are -∞ to 0 or 0 to infinity. Either of these will work. Okay, so then the initial value problem subject to this, when you plug in x naught, you get out each of these specific values. Okay, x naught here equals 0. Has a unique solution for any x naught in the interval. But wait, any x naught in the interval. This x naught does not sit inside any interval that satisfies these conditions because of this leading coefficient equaling 0. God, super weird because it's like the trivial case. It literally equals x. But this could have been, for example, 72x squared or something like that. And it would still be problematic because this leading coefficient equals 0 specifically on the interval, on any interval that this is inside of. I suppose that's the proper way to say it. But yes, this is the condition. This little tricky x naught lies inside the interval such that this is all true. That's the condition that's not being met here. Good.
Sorry, I'm a little confused. So in the example, it says that the interval is -∞ to infinity, right?
Yeah, so it is a
And x
solution.
is 0 within that interval. I don't see how that doesn't violate the, yeah,
So
go ahead.
the trick here is they gave you true information, but they stated it misleadingly. This is a 2-parameter family of solutions on this interval. That's true. Because this y does satisfy this differential equation for any x. However, this interval is not the same as the I that we're talking about here. We're saying in the theorem, if there exists an interval I such that all the a sub i's and g of x are continuous, and the leading coefficient is non-zero on that interval, then this has a unique solution on that interval. So what we need, this x naught does lie inside of this interval, but the rest of these conditions are not met for all of that interval, right? In
Gotcha.
particular, a sub n equals 0 for one of those values. And so that means that we have to take this interval for which it's a solution and slice it up into smaller intervals where they are intervals that satisfy both being a solution and the rest of the theorem's requirements. So we could use negative infinity to 0. We could use 0 to infinity, but literally exactly at this point and nowhere else, this will not have a solution. If x naught had been any other number, this would have a unique solution by the theorem. So it's interesting. Don't get confused when they give you an interval, because they'll do that. This problem is directly from the book, and pretty typical, right? They will tell you that this is an interval where this is a solution. Make sure that you are also checking, does this interval satisfy all of these conditions? If this interval doesn't, how do I have to chop it up into an interval that does satisfy all of these conditions? So this is like, I am a pure mathematician, and I'm here loving this section because it's all theorems and definitions and double checking your assumptions, and that's just some of my favorite parts. Okay, so how many of you have heard of, well, hopefully you've all heard of Wronskian because you've all watched the lecture videos. But how many of you have previous experience with Wronskian? This is actually a really interesting matrix, by the way, for other reasons. Its derivative is extra nice. Okay, so this is complicated notation that you don't have to know, but it is the correct notation. The Wronskian of a set of functions is defined as the determinant of the matrix, where each row lists the functions, all raised to a specific value of derivative. Okay. The beautiful thing is, I remember, I think I was probably in Calc 3, the first time I saw this. And I remember panicking because there's no way I'm going to remember which one is the row and which one is the column and how I'm supposed to write this thing. Like, what if I get it backward and I'm going to get the wrong answer just because I can't tell my left from right. But the beautiful thing about determinants is that the determinant of the transpose is equivalent to the determinant of the matrix itself. So if you mix these up, it's no big deal. You'll get the exact same answer. And if anybody tries to tell you you wrote it wrong, you can tell him to shove off because it's equivalent.
Can you linger for a second on the determinant? I forget. Is there a geometric explanation of what
Yes.
taking a determinant actually does?
Oh God, there is, and I will link you a video to it. But I do not have good words for the geometric interpretation. I think it's 3 Blue 1 Brown that I really
Okay.
like,
Yep.
who has a really good video about it. But I am going to just sort of refresh the low degree determinants. So the way that you can take the determinant of a 2 by 2, it's just saying multiply on the main diagonal, subtract the off diagonal. Like, it looks like a quotient rule almost. The order matters and things like that. But when you start talking about higher level determinants, it starts to get really ugly, really, really fast. In fact, I was going to say exponentially fast. Is that true? Dang, can't think of things quickly enough on the spot. But this gets insanely complicated very quickly because the number of terms in this expansion, and this isn't the only way, this is Laplace expansion or something like that. But there's another way to expand this where you're just talking about all possible permutations of which row and column you've chosen. So you'll have one term where you have this and this and this. And you'll have another term where you have this and this and this, right? So, every possible combination of rows and columns will show up here. That is to say, oh, factorial, that's what I was looking for. It's not exponential, it's factorial. So yes, there will be n factorial number of terms. And it corresponds to the permutation group on a group of size n, which is really cool. That's all pure math, abstract algebra. Woo! But this in particular, it's a little bit complicated because of the pluses and minuses. The way that I remember it specifically is you're expanding it. So the Laplace expansion of this is that you expand a single row. In this case, I chose F1, F2, and F3. But you can choose any of them. If that final row is all zeros, absolutely pick that one. You want to pick the easiest row to work with. Or you can pick a column, right? If F1 is equal to 5 and its derivatives, hence, are both 0, then definitely choose that column to expand on. But what you're doing is you're taking that row or column, and for each of the terms in that row, you're saying, take this entry and then multiply that by the determinant of the things that are left. So delete this row, delete this first column, take the derivative of just f2 prime, f3 prime, f2 double prime, f3 double prime. And so then it just reduces to this, right? So every determinant can be reduced to, or every, say, n degree determinant can be reduced to n multiples of the previous size determinant.
And what determines the sign of the
The way
larger
that
term
I
that you're
think of it
subtracting?
is steps from the first entry.
So it'll just alternate.
Yep, it'll alternate. If you are expanding based on this column, then this one is 2 steps from the original, so it would be positive. This one is 3, vertical and horizontal steps, 1, 2, 3, from the first entry, so it'll be negative. This one is 4 steps from the first entry, so it'll be positive again.
And do only square matrices have a determinant?
Yes, because the way that you would hypothetically handle this with a non-square matrix would be that you would fill it out until it is square, and then that square matrix would have a column of zeros or a row of zeros. Expand on that, and you get this 0 times a thing minus 0 times a thing plus 0 times a thing. And so the determinant of anything with a row of zeros or a column of zeros will always equal 0. All good? This is a little bit complicated. I highly recommend practicing. I have one example where we can run through it quick. But we'll see more of this stuff in this class. So don't feel too far out into the deep waters yet, right? We, for the most, will only ever ask you a 2x2. There will probably be some that are 3x3 that you actually have to check using the Wronskian. But this is a perfectly online class that you can come back and reference this, or you can Google it, or you can use Wolfram Alpha or whatever, right? You can figure out these determinants without having to necessarily memorize what's going on here. But
Do
there
we
are
have access to, do we have access to Wolfram Pro as students?
I have no idea.
Okay.
That'd be nice, but I suspect not, just because I feel like I would have heard of that as a math person.
Right.
If I have access and I haven't been using it, dang. No, I don't think so. But you can always see if you type something in and you want, for example, the step-by-step feature. I know that you can always ask it, okay, show me the first step, and then simplify whatever you had typed to that. and say, okay, solve this for me. Now show me the first step, and it'll guide you through.
That's a
Yeah,
pro
that's a
tip.
hack. That's a hack that I found for myself years ago. But yeah, it totally works as long as the first step isn't too long, essentially, because it'll show you like a specific amount of the solution, not like a specific number of lines. But still, it's a good tip. So yes, definition here. A set of n linearly independent solutions, and we'll, I don't know, especially if you look at the 3 blue, 1 brown video that I will link later. Linearly independent is just saying that you can't, well, we'll say 2 lines are linearly independent, specifically if they only cross at one point. Or don't cross at all?
I think don't cross at all, right?
So.
Because there would be a constant that makes them equal if that were the case.
Yes, yeah. I was trying to like, dang, can I? Well, for the most part, when you're talking about linear equations, you don't ever consider that case because everything has to pass through 0. Um, and so, no, you can't have 2 parallel lines that aren't the same line if everything crosses through 0, 0. So I don't think that parallel lines would be valid. But anyway, this uh, linearly independent for lines is very clear. Linearly independent for a set of more than 2 lines becomes more complicated, right? Because if I'm adding a third line in here, say we're in 3 dimensions, and I add a line like this, the only way to tell if this third line, if this system of 3 lines now is linearly independent, is to say none of these lines lie on the plane formed by the other 2 lines. So, yes, linear independence is just talking about, can you form, is one of these vectors extraneous, essentially? Could we throw something out here and still have as much information as we have? It's useful for finding a basis and trimming down the space that you can talk about to as little necessary information as possible. So linear independence. Okay, but a set of n linearly independent solutions of an nth order homogeneous linear differential equation on some interval is called a fundamental set of solutions, or FSS, often called FSS, on that interval. That is to say, it is totally sort of comprehensive. That is all the information that you need in order to find a general solution, which I think might be after this next example that it says why we care about that. Theorem 4.1.3, if these are specifically the n solutions of nth order homogeneous linear differential equation on this interval I, then the set containing these functions is linearly independent, i.e. a fundamental set of solutions on that interval, if and only if the Wronskian is non-zero for all x on that interval.
Sorry,
So,
lingering on linear independence for a second.
yeah.
2 things. Is it fair to say that if the dot product of 2 vectors is 0, those are linear independent?
Oh, how am I trying to say that? I think that that's correct. I think that's the correct way of thinking about it.
Or like the
It would
projection of
be,
one vector onto the other would be a single point?
oh yeah, certainly.
Okay.
Yep. If you're talking about 2 vectors, it is often very easy to tell if 2 vectors are linearly independent because all that's required there is that one is not the multiple of the other, positive or negative multiple. But when you have a system of more than 2 equations, then suddenly you have to check, okay, pairwise and well, not just pairwise, I suppose. You could just jump straight to the n number. There's no, I think that I have this typed up. Dang, interesting. Anyway, that is just to say that there are no coefficients that you can find that will sum uh, those vectors to 0. If they're linearly independent, then the only solution to C1 times vector 1 plus C2 times vector 2 plus sort of linear algebra, the way that we like to think about it. In this class, I don't think that we linger too long on that phrasing of it, but that is correct. That is the accurate way of thinking about this. So yes, this is a fundamental set of solutions on that specific interval if and only if the Wronskian is non-zero. In the lecture video, Professor Lee specifically calls out that this is often sort of confused with the statement, not truth, that any set of solutions are linearly independent if and only if this is true. That's not the case. This has to be n solutions of the nth order homogeneous linear differential equation. So this is another case of being really careful that all of your assumptions are being met in this theorem, right? If I just give you 3 solutions and I tell you that they are linearly dependent, that doesn't necessarily mean that their Wronskian will equal 0, I think is the way that, because if your Wronskian is non-zero, that does always imply the other direction. Non-zero Wronskian implies linearly independent, always. So that's a good note, because there will be questions that say they just give you 3 of these and say, prove that these are linearly independent. And a good way to do that is to use the Wronskian. So, for example, example 2, determine whether the set x, x minus 1, and x plus 3 is linearly independent on the entire real line. So this is not talking about any kind of differential equation. This is strictly saying, are these objects linearly independent? What is your first thought?
I would do the Wronskian. I would derivate, and then I know that the second derivative of the 3 functions are 0.
Mm-hmm.
So
So thinking about this as a Wronskian, exactly. This is x minus 1, and x plus 3. And there's another way that you can think of this. You don't have to do this via the Wronskian, but that's a really quick way in this case, right? Because the first derivative of all of these will be constant, 1, 1, 1. The second derivative of these will all be 0. And that immediately tells you, I was trying to stress earlier, right, that this determinant will equal 0. So if you have a 0 Wronskian, let's see, not the way that this goes. Oh, right, because this is, maybe I have that. zero Wronskian implies dependent, and so an independent set will imply non-zero Wronskian. Trying to remember, damn. Anyway, when you're working these problems that are n solutions of an nth order homogeneous linear differential equation, at the very least, this is if and only if. I had another internet tab up that had the single direction proof on it, but oh well. But yes, so this Wronskian equals 0. That's one way to tell. But I don't think that that is sufficient going this direction.
Sorry, I'm a little confused. Is when we say, wouldn't this be 3 solutions of an order 1, or am I missing something there?
So in this case, there's no differential equation that we're satisfying.
Mm-hmm.
And so it's a little bit strange. This particular theorem doesn't technically apply.
Required to be linearly dependent?
So the problem with that is exactly the pure mathematician in me saying that you have to check your assumptions. You got to check what assumptions you're using here, because for this theorem to apply, you have to be talking about a fundamental set of solutions to an nth order homogeneous linear differential equation. And so I'm sure that I could dream up a third order homogeneous linear differential equation that these are the solution to. I'm pretty sure that it will be if and only if for these. But technically, on just a blank page, here's a set of objects, tell me whether they're linearly independent. That's not an if and only if.
Gotcha.
Let's see if I can. Wronskian linearly independent. Yes, I had Googled this earlier. Uh, yep, 3.6 linearly independence in the Wronskian. Linear. Here it is. Examples theorem. This is the general theorem. If these are differentiable, right, so the Wronskian exists, of these is non-zero for some x naught on an interval, then f and g are linearly independent on that interval. Oh no, this is the, it is if and only if for a 2x2 case. Okay, so then I swear that I saw one that was in higher dimensions that was just the, okay, well, fine. At the very least, Professor Lee's got me all psyched out. He said lots of people mistake this for an if and only if when it's not, in a case where it's not. But no, yeah, this is totally just a one direction. Okay, yes. If Wronskian is non-zero, then these are linearly independent. Therefore, by contrapositive, if any of you have taken fun foundations of mathematics, by contrapositive, if these are linearly dependent, then the Wronskian must equal 0. So if you do the Wronskian and it comes out as non-zero, you can conclude that these are linearly independent. However, if you do the Wronskian and it comes out as 0, that is inconclusive. Does that make sense? I don't know. Do you folks have foundation of mathematics background? Logic sets and proofs is just my dearest love in the universe. But this is just saying P implies Q, and equivalently, not Q, what's the proper notation here? Not Q implies not P, right? These are equivalent statements. But from this information, you cannot conclude, well, in particular, that Q implies P. You can't turn this implication around, logically speaking. So in this case, we come out with this Wronskian equals 0. That's not sufficient to say that these objects are linearly dependent, even though they are, having knowledge of the problem. Have I lost everyone yet?
A little bit.
Yeah, so this is definitely logic type stuff, but specifically what Professor Lee is trying to say and what this is saying is that if you calculate the Wronskian and it's non-zero over an interval, then you know that those functions are independent of each other on that interval.
So
That
this is
implication
to say that there are independent functions with a 0 Wronskian.
Yes,
Okay.
that is a concise and accurate phrasing. There exist functions which are independent of each other, but still have a 0 Wronskian. It would be interesting to try to think one up. It shouldn't be too hard, but oh well.
So then how do we solve this example 2 then? If the Wronskian, or no, sorry, the Wronskian is enough here.
The Wronskian won't work here. Yes,
Oh, no,
exactly.
it's not enough. Shit.
Ideally,
I mean, excuse me.
yeah. If it equals 0, then it won't be sufficient. That's the problem. Yes, so this is inconclusive. See my little dot there. Supposed to be a face. Anyway, so in this problem, the way that I solved it at least, was just to recognize that I can apply this other definition of linear independence, right? Can I represent one of these quote unquote vectors as the linear combination of the rest of them, where one of these coefficients, at least, is non-zero? So we have x and x minus 1 and x plus 3. If I want to represent one of these as a sum of the other two, how could I go about that?
Multiply the first term by 2, the second one by -3, and the second one by -1, or the third one by -1. Maybe.
Let's see. Oh, are you saying -1 over here?
Yeah, yeah.
The other side. I see. I was like, -1, that's great. I'll just put an equal sign. Okay. So when we do this, we come out with -3x plus 2x will give us -x appropriately. And -3 times -1 is a positive 3. Is that right? -3x plus 3. Dang, not quite. That's really close. It's -x plus 3. The way that I did it the first time was not the easiest way to go about it. But what I know is that I get, how did I set it up? I wanted to use negative 3. Right, okay, so you have the right idea, but this, what I'm trying to say is this negative 3 was good intuition, right? But you don't actually need this negative 1 over here. You want to leave that positive. So negative 3 x minus 1 is equal to x plus 3. So this will be negative 3x plus 3. Now, how many x's do I have to add to this to get x plus 3? I just need 6, right? I want 6. No, that's 3x. 4? Here we go. Right? So if I have 4x minus 3x plus 3 will give me x plus 3. I think that this is the simplest way to go about it, dealing with the more complicated terms, x minus 1 and x plus 3 first, and then saying, like, whatever I need to happen, all I need, these are the two that have constants involved. So what I need is to figure out how I can sum these up so that this sum of constants will equal this sum of constants, right? So if this was, x minus 2 and x plus 5, then it might be a little different. I need to multiply a 2 over here and multiply a 5 over here or whatever. But I know that I have this x over here that I can just tack on whatever multiplier I need to settle that variable down to 1 in this case. So however this multiplier messes up this x, I can just fix that by offsetting that here with this multiplier. So that's, I think, the quickest, easiest way. And so this is to say that one of these, there exists, you don't have to write this all out by any means, there exists C1 equal to 4, C2 equal to negative 3, C3 equal to negative 1, such that F1, yes, C1 F1 plus C2 F2 plus C3 F3 equals 0. Therefore, these are dependent on each other. You could throw one of these out, maybe not any one of them, right? All we know is that at the very least, x plus 3 is more information than we need, because we can represent it using the rest of our information. So that is sort of analogous to having this third line that lies on the plane of the other two. Oh, that's off the frame. Here we go. Right? Similar to say that when you take some multiple of this one and some multiple of this one and add them together, you get out this line. So, in conclusion, this is not linearly independent on the entire real line. In fact, I believe for any value x, okay, if this is a fundamental set of solutions on some interval I for a homogeneous differential equation, then the general solution of that homogeneous linear differential equation on I can be written as a linear combination of those solutions. So this is the super important, valuable part of this idea of fundamental solutions, right? And using the Wronskian to double check that they're independent and things like that, right? This fundamental set of solutions gives us a general solution. That is to say that every solution of this differential equation can be expressed in this form. And the textbook has an interesting example using hyperbolic sine and cosine, but I don't have any experience with those, so I'm not going to go into it. But it is interesting, representing those as e raised to some power, some sum of e's raised to a power. It's very interesting. And if you're curious about hyperbolic sine and cosine, you should totally read your textbook because it's cool. This theorem. Okay, this one is a lot to read just because I have the standard form of a homogeneous and non-homogeneous differential equation specifically explicitly stated. But this is to say, if you have the general solution using a fundamental solution set, if you have the general solution of the homogeneous linear differential equation, and you find literally any function that works as a solution to the non-homogeneous differential equation, then the general solution of the non-homogeneous linear differential equation is the sum of those two, this general solution to the homogeneous equation plus the particular solution, which makes sense, right? The general solution to this homogeneous one will have equals 0 on the right side. And so if you add a particular solution, y sub p to it, then you should get out 0 plus g of x, right? Equal to g of x. So it should be a general solution to this non-homogeneous equation. And that turns out to be the case. This is often written as y sub h plus y sub p, where y sub h denotes the homogeneous general solution, and y sub p denotes the particular solution to the non-homogeneous equation. So this is a mouthful. Do you feel like you understand this well enough? Oh, it's 3:06. Wow, okay. Just saw the time. Okay, so maybe let's hop through the last couple examples. Verify that the two-parameter family of functions, this is a general solution to the non-homogeneous linear differential equation, this. So that consists of showing, let's see, search for your constants here, because they'll tell you what the fundamental set of solutions was, right? There has to be an arbitrary constant attached to each of the fundamental solutions. So y equal to c1 times e to the 2x plus c2 times x e to the 2x plus x minus 2. This tells us that, did I miss one? Dang it, it did. Also plus x squared e to the 2x. Okay, this tells us that we have an arbitrary constant here attached to our first fundamental solution. We have an arbitrary constant here attached to a second fundamental solution. And everything that doesn't have an arbitrary constant attached, all of this is talking about your particular solution, y sub p. So this first half is y sub h, and that second bit is y sub p. What this is saying is you have y1 equal to e to the 2x, and y2 equal to x e to the 2x. So to verify that this is in fact the general solution, we have a few things we would need to check. We need to say, are these both solutions to the homogeneous, the associated homogeneous differential equation? Question mark. Is this a particular solution? Is this a solution to the non-homogeneous? And that's just a matter of taking the derivatives and plugging it in, right? Adding it up and everything. And are these linearly independent? These are the 3 questions that we have to answer. Usually, I don't know, they're not in any particular order, but I suppose I most often approach them as 1, 2, 3. Right? So in this case, this is just a matter of being able to read this problem and dissect, sort of extract the information that we need to get out of it. Right? Catch these arbitrary constants, and whatever they're being multiplied by, that is one of the solutions that you're expected to check. And anything that doesn't have an arbitrary constant attached to it falls into this y sub p, that you just need to check whether that's a solution to the non-homogeneous differential equation. So the homogeneous differential equation here is y double prime minus 4y prime plus 4y equals 0, right? And so this should be quick enough to check. I'm going to let you handle that yourselves. It should be the case that this is, it says verify that this is true. It is the case that this will be the general solution to this non-homogeneous differential equation. Okay, and the last and most important theorem, which I sort of mentioned when I was reading that last theorem, is that if this is definitely written complicatedly, so I want to translate. If you have a number of particular solutions to the linear differential equation here, where they don't necessarily have the same g of x, right? You have, say, k of them, and you have k different g of x's corresponding to each particular solution. So say you have something where g of x equals 0, you have a particular solution where g of x equals x, and things like that. Then this linear combination of those particular solutions is itself a particular solution to this non-homogeneous differential equation where g of x is the linear combination with the same constants of those g sub I of x's. I'm going to take a breath and I'm going to say that again. If you have k particular solutions corresponding to k different non-homogeneous differential equations where the left-hand side matches, then the linear combination, a linear combination of them with any set of constants, is itself a particular solution to this non-homogeneous differential equation with a corresponding linear combination of the g of x's. In particular, any linear combination of a homogeneous solution is itself a solution to the homogeneous differential equation. Because of course, if these are all solutions to a homogeneous differential equation, then all of those g sub I of x's is 0. Are 0? All of them are 0. Right? And so any linear combination of them will itself also equal 0. So that is just to say, if you have k solutions of a homogeneous thing, then any linear combination of them is also a solution to the homogeneous. And this, of course, means that y equal to 0 is a particular solution to every homogeneous linear differential equation, just like we were saying, in a typical vector field. Every vector goes through 0, 0. In the same way, in a homogeneous system, 0, 0 is always going to be a solution. Okay, very last example, just coming on that last theorem. By inspection, find a particular solution of this. And so I'm not going to write out the particular solutions. I don't think I solved for these. They're supposed to be very short anyway. But a solution of this sum equaling 10. Okay, if you find a solution to this linear equation and this linear equation, then the sum of those things, just a flat sum, is going to be a particular solution to this differential equation because the left-hand side matches and the right-hand side is a linear combination of these two. And then, final thing, you can actually do this with any linear combination. So think about what it would take to turn a particular solution for this using a sum of these particular solutions into a linear combination of these, where you're taking, would it be -2 times the first and 1/2 times the second? This turning a -4x into 8x and 10 into 5, right? Just because these are separate with the constant and the variable, I know that you can do that. Okay, any questions? In that case, you shared this link. Let's see. I'm going to trust you on it and open it in my shared information tab. Okay.
Yeah, so this is not particularly related to what we're doing. This is only if you wanted to spend some time looking at something that had me stumped.
Yeah.
It's a derivation of multiple regression, and part of it involves this complicated partial derivative that I couldn't follow. It's at the bottom
Okay.
of page 2, if you're curious.
Yeah.
Yeah, so there's this rule right here. If you see db prime a b del b equals 2ab
Okay.
equals 2b prime a, that is a equality that I have not personally been able to derive, and I was wondering if you have any lucidity here that I otherwise cannot find.
Let's see. Well, I'm going to say the other two of you can totally leave and not bother with this all. And have a good rest of your day. And if you have any more questions on the material, especially with the problem set, please email or use the questions forum, or I don't know, get phone numbers of your classmates and text them or whatever. But make sure that you get those problem sets done and make sure that you're confident in your answers, right? Because there's no reason not to check.
Thank you, Jasmine. Bye.
Yeah. See ya.
Yeah, thank you.
Yeah, have a good day.
Hey.
Okay. And I'm going to stop.
So, yeah, so in this problem,